This was 7. About to be a little bit higher than 7. Okay. We should be scared.
So we've had a lot of before.
Excuse me.
But we have something to speak to. Let's get to this.
Question 7. Problem 8.
No, that's. I think that's good.
Okay.
I usually study before I go. So, I'm studying that's like this.
All right. The potential energy of two atoms in a diatomic molecule is approximated by U of R, A over R to the 12th minus B over R to the 6th, where R is the spacing between the atoms and A and B are positive constants. Find the force on one atom as a function of R. Okay, so
So I understand how part A is done. It's just it's a negative gradient, right?
yep. Yeah, so here there's one dimension, so it just boils down to minus the derivative, right? But yeah. Yeah, so okay, the force then minus du dr, so you can just differentiate that, and, right? I mean, you guys can see it's 12 times a over r to the 13 plus 6 times b over r to the 7th, right? Because these are reciprocals, when you differentiate a reciprocal, it adds to the exponent, right? I mean, you could say that this is, if you're having trouble with the differentiation, almost certainly you should make this step a times r to the what? Negative 12, right? Plus b times r to the what? Negative 6. And so forth. So, what was your question about it then?
For the distance between the equilibrium distance.
Equilibrium
How do you find that?
distance. Let's see here. So, are you given A and B? A and B are positive constants, huh? Let's see here. So the method that I would try on the basis of what I've already told you guys, I would look at U, which is A over R to the 12th, right? Plus B over R to the 6th. Minus?
Yeah.
Oh, well then you guys should have corrected me here. I guess some of you did. Okay. All right, so if I do that, is there anything I can factor out here?
Oh, yeah. 1 over R6.
1 over R to the 12th? Okay, yeah. I'm ignoring you guys. I mean, you're right. You could factor out R to the 6th, but if you do this, it's more fun, right? Because then you've got A minus what?
BR to the 6.
BR to the 6th, right? Oh, this doesn't really help us either, though. Where are equilibriums? I mean, this will tell me where the potential is 0. Is potential energy 0 have any kind of deep physical significance? Not really, in general. I mean, it could in a specific example where you've made the potential to be 0 someplace significant. But for an arbitrary problem, where are the equilibriums? Like here, right? If I'm graphing U versus whatever. So really you're looking for what? What are these? These are places where what?
Forces equilibrium.
Yeah, the force is zero at possible equilibriums, right? So we should really set whatever we get up there equal to zero and see where that leads us, right? Okay, so, but we can kind of do the same calculation. Let's see here. So this is, portions. Oh well. So what's this work out to? We have what? Minus 12 over a r to the 13th.
The A's on top.
Yeah, why is it?
Oh, I'm sorry. Good job. How many minuses do I have? Minus, three minuses. Minus 6b over r to the 7th. So if you look at that, you can factor out, I would factor out an r to the 13th. And then I can look at it this way. That's minus 12a.
The 12A should be positive, though, shouldn't
Oh,
it?
should it? I don't
Well,
know.
because there's a negative out in front, so.
It's just minus.
And then minus 12, so. it's
Minus in the derivative.
So
It'd be
Well, it should
positive.
be positive, yeah. Thanks. There we go. Cool. So 12a minus what?
6B over the 6.
All right.
Could you pull out another 6 too?
Yeah, sure. Okay, I'll do that. Sure, why not? It's here 6 over r to the 13th. 2a minus 3b r to the 6th.
Just,
What I did? Oh, 1. I'm an idiot. Yeah, thanks. All right, finally. I think I made that error now. So we're looking for part, was that part B? Equilibrium distance. Yeah, so we want to find that equal to 0, right? Now so how can you have this, why did I factor this out? It was just so that I can understand where it's 0, right? Like r equals to 0 doesn't give you 0, it gives you, r equals 0 is undefined, right? So it must be that the thing in brackets is 0, right? So you just solve that equal to 0, what does that give you? So you can solve for r, right?
Yeah. 2 6.
Yeah.
6 over B.
Right, exactly. Which is what he has there, yeah, to 6 through to 2a over b. Is the equilibrium stable? He says yes. How do we know that? Second derivative test? Yeah, you can do that. That sounds fun. But
That is graphing.
Fastest way to do it.
better than graphing. Well, there are other ways. There's only 1 0, right? There's only 1 0 in the force, right? So if you look at the sign chart of du dx with a minus, right? So 0 is kind of not even allowed, right? And then you've got this critical point, which we just said was what, the 6th root of, finish this, r to 6 equals 2a over b. So, 2a over b, 6th root, right? That's a specific thing, A and b are positive constants, that's some value. And then you can just think about, is it increasing, is the force increasing or decreasing, like, to one side of the maximum or the, right? I mean, for example, if I plug in less than this value, does this quantity become positive or negative? for example, what happens if I put A over B? To the sixth root of A over B, what do I get then? I get 2 minus A. It's positive, right? And then if I put something, for example, like 3A over B, sixth root, and then I get something negative, right? So that means you're increasing as you approach it from one side and you're decreasing it. Oh, sorry. This tells me about the graph of minus u, doesn't it? Yes. So, but that's what you want for the force, right? But you want the force to be pushing you this way from that side and pushing you that way from that side. That's a stable equilibrium for the force, right? In terms of straight calculus 1 first derivative test, I should really look at du dx if I want to see things about this being a minimum for the graph of u. In other words, be careful with your thinking about the minus sign here because it will mess up some of your naive calculus thinking if you're not careful. Not naive, just not cluttered by this physical minus sign. Okay, other questions? I've now spent entirely too much time on this one. Amy.
You do part C and D.
It's part C and D of this one?
Yeah.
See here, suppose the distance between the two, let me erase this stuff, okay. Probably I'll regret it, but. Why is there so much wind noise in here today?
Could
What's
be
that?
construction.
Is it construction?
It doesn't sound like wind because we're in the middle of the woods.
Does it somehow suck in the construction noise from outside? Is that what's happening?
Probably.
It's weird.
I mean, it is kind of windy outside though.
Sorry, I stopped distracting us. Suppose the distance between the two atoms equal to the equilibrium distance found in part B. What's the minimum energy that must be added to the molecule to disassociate it? That is, separate the two atoms to an infinite distance apart. This is called the disassociation energy of the molecule. All right, so so you have that molecule, the other molecule, right? And this one, X is what? X is equal to, not X, excuse me, R is equal to what would we say, the sixth root, 2a over b, is that it? Okay, so that makes it, that's the equilibrium position. And so they're asking us what? How much more energy do we need to add to the system in order to disassociate them, right? So U of R was equal to, let's see here, what was it? It was A over R to the 12th minus B over R to the 6th, right? And, so, let's see here. This is really, let's see here, 1 over R to the 12th, right? Times A minus B times R to the 6th, is that right? I mean, here's where I'm going with this, guys. So if the potential energy looked like this, right? If this was actually the graph of the potential energy, if I want to, I don't know, maybe it looks like this. That's probably a better picture. All right. Suppose that the picture was like this. I'm not saying it is, just suppose it was, okay? If that was the case, then the equilibrium position would be like here. Call it R naught. Right, and they're asking how much more energy do you have to give the, let's say this particle, this part of the molecule, right? Molecules, two atoms put together, or more. in order for it to be free, for it to disassociate from the other mass, so say it's M1, M2 for the sake of discussion, how much more energy do you have to give to the M2 in order that it's not even coupled to M1 anymore, that just can just travel off and off and off and off, right? Well, we learned in terms of energy diagrams was that, you know, for these kind of total energies, it's not going to be dissociated, right? It's just going to travel back and forth, bouncing back and forth like a spring, right? But once you get up to this magical point right here, then it can just go away forever and ever, never come back, right? So it would be disassociated if it got to that energy level. So the question really boils down to this. What is the maximum potential energy, maximum potential for R greater than 0? R equals to 0 is not interesting, right? That's just the divergence that comes from imagining the molecules are in the exact same place. I mean, the atoms are in the same place. Math breaks down there. So what is the maximum U for that?
You solve for the derivative of this. You know, the zero derivative, so there's no peak point, right?
Right. So my picture might be wrong, right? What's the other thing that it could have looked like? Like we were talking about gravity the other day? Maybe the picture actually looks more like... How would that go? Well, apparently there's a stable equilibrium, right? Oh, that can't be. Wait a minute. As R goes to 0, are A and B both positive constants?
Yes.
Okay, so it spikes up like this. Because this dominates. This is huge when R is really small. This is a huge positive constant term for like R equal to like a billionth or something, right? This is nothing. As R goes to 0 from the right. So it's got an inverted asymptote there. And there's no other place where it does what? Yeah. What's the limit as R goes to infinity of U of R? What's it go to? Yeah, it goes to 0, right? So can it do this? They can't though, because we already found that there's no one of these. Right? It's only got one max. It's got that one local max. So it must be the shape of the curve looks like this. Because it asymptotically goes to 0, right? So, in other words, if you set U equals to 0, let's see here how to say this. So U of R equals to 0, that will give me what? Oh, that's not what I want to say. Sorry. I'm an idiot. Shut up. Erase some of this stuff. How to say this? Let's say this. So we have. You have U. U of R naught is your potential energy, right? If you're at rest at the equilibrium, you just sit there, right? But you want to have enough energy to have your energy level be what? Your energy level you're interested in, the minimum dissociated energy. The argument I just gave you says the minimum dissociation energy is total energy 0, right? So you want U of R naught plus some value to get U equals 0, right? Plus kinetic energy equals to 0, because that's the total energy, which is just enough to escape the potential well that you're in, as R goes to infinity. So what's that make kinetic energy then? You said 1/2 mv squared equal to minus U of R naught, which is okay because U of R naught's a negative value. What are we supposed to find? The energy? Yeah, so the energy is minus U of R naught. Oh, excuse me. What minimum energy must be added? It is exactly this energy, magnitude of this, right? Yeah. Oh, that's stretching. Sorry. That wasn't a question. Okay, so more to the point, what is U of R naught? That is actually, you plug in this into the formula, right? So you gotta do A times, well, A over 2A over B to the 1/6 power to the what? To the 12 minus B over 2A over B to the 1/6 power to the 6th power. And then you gotta clean this thing up and take the negative of that. That would be the energy that should be added. Peace. Apparently, minus B squared. What?
Minus B squared over 4A.
It says minus B squared over 4A. What do you know, like? Sorry, that's.
So is that taking away energy?
That doesn't make sense. Minus B squared over 2A is added. A and B are giving you positive constants here. That's not an added energy, that's subtracted energy. I do think that's what you'll get from setting U equal to 0.
How do you take away energy and that moves them apart in infinite distance?
No, what I'm saying is I don't believe this answer. I think you should add that energy without the minus. I think you should add B squared over 4A if I had to guess. And that would be enough energy to disassociate them. I think when we work this out, this U of R naught, I think that this is going to exactly give us minus B over 4A. B squared over 4A. Like, do the math here, what do you get?
Yeah, that's it.
Oh. Really?
It comes out to B squared over 4A minus B squared over 2A.
B squared over 4A minus B squared over 2A?
Yes. That turns into minus B squared over 4A.
Right. But you see, that's not the energy added. That's the hole you're in. This is minus B squared over 4A. So I totally disagree with the answer here. This is wrong for his wording, unless I'm reading this wrong. Minimum energy that must be added to the molecules of disassociating. Oh, I'm sorry. He's saying find the change in U. Fine. All right. He's right. We're wrong. Whatever. All right. Anyway, let's go on. Other questions? But what's more important than the specific mathematical details of that problem is the general idea of the connection between the potential energy and the force, right? You want to understand that interplay. What's that? Which number?
Number 10.
Oh, duh. Well, this should be a welcome break, given the last problem. On a horizontal surface, a crate with mass 54.5 kilograms is placed against a spring that stores 396 joules of energy. The spring is released. The crate slides 5.79 meters before coming to rest. What is the speed of the crate when it's 1.98 meters from its initial position? Oh, right. See if I can do this one. All right, so the idea here, let's see, let's draw a picture. What do I got here? So, oh, the spring, they don't even tell us the spring constant or anything, they don't care, right? I mean, we just got a wall, whatever, spring, the spring is compressed. There's this mass sitting here, M, and so the initial energy, what's the initial energy? Well, it's at rest, right? So the energy of the system, it's all in the spring, right? And it's 396 joules. And then the spring springs, and then you're over here, right? And in this intermediate position, you've got some velocity, say like that, I'll call it v1, right? And you've gone some distance, let's say d1. Your energy is no longer 396 joules, right? We're assuming the spring has no mass. All of the energy transfers to the box in the form of kinetic energy as the mass leaves the spring, okay? That's our assumption. So over here at this middle point, your E1 is equal to E naught minus the energy lost to friction. What is the energy lost to friction here? Force times distance works here. That's that simple case. So what's the friction force? It's force of friction times D1. But what is that actually? Force of friction should be mu mg because that's the normal force. It's just weight here, and D1. Okay. Agree? You should also agree that there's no potential energy that's interesting here besides the original energy of the spring. And once that's done, it's done. Certainly there's no potential energy at event 1, right? So the total energy is also equal to the kinetic energy. So this would be equal to, 1/2 mv1 squared. There's one other thing we're given in this problem, right? Which is what? It comes to rest somewhere, right? So like over here, its final velocity is 0, it's at rest, right? And that distance is d2, right? And we're actually given that, 5.79 meters. Now, how is E2 related to everything else? E2 is equal to what? Well, it's also equal to E naught minus the energy lost to friction, right? So minus the force of friction, which is what? Mu mg. That's the force of friction n times d2, though, right? What's the energy? What is E2, though? There's no potential energy to speak of here. How much energy at the end? Yeah? None? 0, right? So this is equal to 0. So what does that tell us? What do we know here? Let me underline the things which are given. We already know E naught is 396. I think we were told the mass of the box, were we?
Yes.
Yeah, this is what, 54.5 kilograms. So we know this. Gravity, well, gravity. We know D2. Hey, check it out. Now, you're like, but they never told me what the coefficient of friction was. That's true. That's because you have to use algebra to discover it. There it is. So mu is equal to, what is it equal to? It's equal to E naught divided by mgd2. But you know all those things, so you can figure that out, right? And then what? What we asked for is the speed, v1, right? Our goal was to find v1, right? So you know, I see I can do is I can say, well, V1 is equal to, you know, 2 E naught minus 2 mu m g d1 all divided by m square rooted, right? So plug that stuff in. And so I guess if you wanted to like never find that symbolically, you could just like plug this into there, and that would be even more fun. I'm going to resist to say urge to say more about this. I think I've shown you enough that you can solve it now, yes? No? The key is to look at the three events that you're given. The start, the middle, and the end, right? Energy's not conserved here because there's friction, but the energy is lost in a very systematic way due to the work done by friction. So. Any questions? Sorry, someone stole my calculator.
So good. I'm thinking of that data side.
Ah! Someone put my calculator back where it doesn't belong. It's okay. Bailey's leaving us soon. We won't have her to pick on for a little bit. She'll come back. I guess that means your second test will probably be harder since she won't be here. So the mu I get is about 0.128. Just as a ballpark for you guys as you're working out your problem. So obviously the speed I get is 3.09 from my numbers. Your numbers will be a little bit different, but kind of ballpark. Okay. It's good. That's the question, what's the velocity when you're there? D1 is, oh, I actually brought that under. D1 is equal to 1.98. Next question? No, the same mission?
Yes.
Is this the one where I tried to do it the wrong way?
Yes.
What, I already talked about this?
Yes.
Yeah.
So. To recap, the truck loading a station post office is 1.1 kilogram package released from rest at point A on a track that has a quarter circle radius of 1.6 meters. Size of the package is small. Treated particle slides on the track, reaches point B with a speed of 4.3 meters per second. From point B, it slides on a level surface distance 3.3 meters to point C where it comes to rest. Apparently there's friction. Excuse me. What's the question? I guess we're not told that there's no friction. What's the coefficient of friction?
How do you solve
Am I told the speed at B?
Yes.
Yeah, and it comes to rest at C. Okay, so, you know. So it's kind of the same as this one we're just talking about here, right? I mean, if you look at B and C, so you got 4.3 meters per second here, right? Point B. At point C, you got 0 meters per second. So your initial energy is equal to 1/2 m times 4.3 squared. And that is going to be equal to the energy lost, right? I mean, that's equal to whatever the distance was. What would it be? That's given, right? 3.3 3.3, I'll need to write out symbolically, is equal to the force of friction, which is mu mg in this case, times d. Let's see here, we don't need to know m. What are we trying to find? Coefficient of kinetic friction. So that tells us that mu is equal to 1/2 of 4.3 squared divided by, let's see here, g, which was 9.8, and d, which was 3.3 meters. I put everything in meters and kilograms and seconds, so this should work out. Do any conversion? Oh, yeah, 0.286. So what was the question? Was the question about part A or part B? Or the what? Here.
I was confused on both.
Oh, okay. So the first part really is just, I have an initial kinetic energy. I'm losing energy due to friction, right? So at the end, it's at rest. So all my energy's gone. Where has it gone from? I mean, it's gone from the work done by friction, right? So I can set the total energy at the beginning equal to the work done by friction. Talking in terms of magnitudes, obviously. I mean, the work done by friction is negative. So, I mean, technically, the energy final is equal to the initial energy plus the work done by friction. But the work done by friction is negative, so the work done by friction is actually equal to, the minus E naught, essentially. So that's why I can just set the initial energy 1/2 mv squared equal to the friction magnitude. Ow! There's a sharp corner on something down here. Oh well. Okay, so that makes sense for part A. For part B, how much work is done by the package, done on the package by friction as it slides down the circular, or from A to B? Well, it starts at rest, right? So, as you consider this part of the motion, right? You have to say, okay, well, where did the hypothetically, if there was no friction, you'd have more energy, right? So whatever energy you lost must be due to friction, right? More to the point here, the energy at B is equal to the energy at A, right? Plus the work done by friction, going from B to A, right? So what's the energy at B? Energy at B is 1/2 m times 4.3 squared, right? Is there any potential energy there? Not really, no, right? Up at the top here, though, you have VA equals to 0. They told us it starts from rest. And you have mg, the height at A, right? What's the height here? Yeah, it's r, right? Because if r is the radius, it's also the height. If you look at this distance, it's the same as that distance, right? So if you look at it, the height is r. So mgr plus the work done by friction. So work done by friction will be equal to 1/2 m times 4.3 squared minus mgr. I hope they told us what the mass. They told us what the mass was, didn't they? So on the mass is 0.1. I have that the radius was whatever it was, 1.6 meters. I know gravity, so I can calculate that, and it works out to minus 6.44 joules. Does that make sense? I wouldn't try to quantify that in terms of a coefficient because it's kind of a complicated thing. I guess you you could come up with some sort of like macroscopic description, like take the arc length of it, and you could set that equal to like arc length times the average normal force. I don't know. The normal force is 0 to start with, right? And then it increases to its maximum. We actually worked that out the other day. I foolishly tried to solve this directly in terms of like Newton's laws and solving a differential equation or something. It was really awful. I recall. This is a better way to think about it. It's good that you asked about this again, actually. As you can see, adopting the viewpoint one of you suggested is far easier. People say knowledge is power. It's only partly true. Sometimes knowing something is hurtful.
I thought you were going for a pun on power. Is it on second?
No, it's not good. Not a funny thing. Other questions? 11 on 6. If I can find it. All right. The aircraft carrier JK has a mass of 74 million kilograms. When its engines are developing their full power of 280,000 horsepower, the JFK travels at its top speed of 35 knots, which is otherwise known as 65 kilometers an hour. If 74% of the power outputs of the engines is applied to pushing the ship through the water, what's the magnitude of the water resistance that opposes the carrier's motion at this speed? All right, so let's see here. You got the ship, and here's the force of the engines. Applied. Now, this, of course, is the force of friction. Supposing the velocity is like this, 65 kilometers per hour. Right, otherwise known as 65 kilometers over hour. 74% of the power output of the engine is applied. So this actually, the force of the engines actually applies to the water, only 74%, right? From 74% of power, right? So that means actually you only get a power of what? 74% of the 280,000 horsepower, right? Which is what, like, so something like 207.2 for me, 207.2, well, 207,200 horsepower for the power. Now, that is equal to the force that's actually applied from the engines, right? Times the velocity of the boat. Because power is force times velocity, right? Oh, yeah, so you can find that the F applied is what? 207,200 horsepower. The divided by the V, which is 65 kilometers per hour. Right? And that, by the way, will be equal in magnitude to the force of friction, right? Because why? Because the boat is going 65 kilometers per hour, is not accelerating. That means that that is the point at which the engines have reached an equilibrium with the friction force of the water, right? It is sped up to that maximum top cruising speed, and the friction force of the water is exactly balanced by the force of the engine going forward. So that's why I know that the force of friction and the force of the engines that's actually applied to the water, the 74% of the power, those are equal, right? So you just got to calculate 207,200 horsepower divided by 65 kilometers per hour. How do you do that? Yes, much convergence.
Wolf from Alpha.
Oh, unfortunately we're out of time. Oh. Same power output. Real good at convergence, very much. I'm just saying.